Hello students, welcome to Basic Electrical Engineering lectures. Today's lecture is on RLC Series Circuit. I am Mr. Nagaraj DC, Assistant Professor, Department of EEE, BMS ITM Bangalore. So in the previous lectures we have seen Series RL Circuit and Series RC Circuit. In this lecture we will be looking into the Series RLC Circuit. What is the nature of RLC circuit when connected with when connected to the alternating current supply, which is sinusoidal in nature. Okay. A series RLC circuit consists of a resistance component R, inductive component L and capacitive component C connected in series across the supply of E volts. So need not to mention here that capital E is the RMS value of supply voltage, capital I is the RMS value of circuit current. Okay. So whereas the supply voltage is given as E equal to Em sin omega t. So with this equation of instantaneous equation of voltage, I am considering the initial phase angle of voltage to be 0. It means that I am considering the voltage on a reference axis. With respect to this voltage, I would like to know what is the phasor relation of this current, okay, in this circuit. Okay. So in previous circuits, what we have seen, in pure circuits, the circuit was either pure resistive or pure inductive or pure capacitive. In practical circuits, the circuit was either inductive with certain amount of resistance in it or capacitive with certain amount of resistance in it. Okay. Whereas in this circuit the components are R, L and C. All the three components are existing in this circuit. So it is difficult to us to say whether the behavior of the circuit is resistive or inductive or capacitive, because the effect of resistance is also present, effect of inductance is also present, effect of capacitance is also present. Okay. So ultimately the nature of RLC series circuit can be known only when I know what are the values of these resistance, inductance or capacitance, or what are the effects of resistance, inductance and capacitance, and which of the components are prominently having its effect in the circuit operation. Okay. So here if resistance is very large, okay, inductance and capacitance are very low, then the circuit may behave resistive. If inductance is very large, resistance and capacitance is very low, therefore the circuit may behave inductive. Similarly, if capacitance is very large, then the circuit may behave capacitive with very low values of R and L. So to decide this, I need to observe different cases in analyzing the RLC series circuit. So there are three possibilities to understand the nature of the circuit. The first, if the inductive reactance is greater than capacitive reactance, that is if XL is greater than XC or XC is lesser than XL. Now the question is, why we are discussing only with respect to XL and XC? Okay. Why not we are taking R into consideration? So guys, please remember that the reactances of inductance or capacitance are depending upon the frequency, whereas the value of resistance is forever constant once it is used in the circuit. So the value of inductive reactance and the value of capacitive reactance will vary with respect to frequency. Therefore, if the frequency of the supply source is varied, then the effect of circuit may be different at different frequency ranges. So you might have already studied the resonance, series resonance circuit. In that case, you have studied XL is equal to XC is the condition when series resonance occurs. That is the point when the current in the circuit reaches to the maximum value, or it is the highest magnitude at XL equal to XC. So we will come to that point when we see what happens with an XL equal to XC. So the first possibility or first case is that the inductive reactance may be larger than capacitive reactance. Second possibility is capacitive reactance may be larger than inductive reactance. And third possibility is both reactances can be equal. Now when XL is greater than XC, what is the nature of the circuit? We will analyze. When XC is greater than XL, what is the nature of circuit? We will analyze. And when XL is equal to XC, what is the nature of circuit? We will analyze. So let us consider case 1 where XL is greater than XC. Okay, that is inductive reactance is greater than or is having more value than capacitive reactance. So with this, okay, if XL is greater than XC, then you can observe the voltage across L is I into XL which is EL, and voltage across C is I into XC which is EC. So very clearly my EL will be larger than EC. If XL is greater than XC, my EL is greater than EC. Therefore, I into XL is greater than I into XC. Okay, so it is evident that because I is same through L and C and R, therefore if XL is greater than XC, my I into XL will be obviously greater than I into XC. So let us see how the vector diagram is drawn for this circuit, because when I draw the vector diagram, then only I will understand the exact nature of the circuit, whether the circuit is inductive or whether the circuit is capacitive or whether the circuit is resistive. Okay. So to draw the vector diagram, like I have shared already in the previous lectures, the thumb rule is that whichever the quantity that I represent in the form of a vector remains common across all the components or through all the components of the circuit, I take that quantity as the reference vector. So this is a series circuit, therefore we know current will remain common through all the components connected in this circuit. So I take current to be a reference vector to draw the vector diagram. Okay. So don't get confused with E equal to M sin omega t. I told in the previous point that I take voltage from a reference axis. Okay. So what I am doing here is I am simply taking the initial phase angle of voltage starting at 0 for my convenience. But whereas the rule for drawing the vector diagram for any series circuit is that the common quantity that remains in all the components same, that quantity to be taken as reference vector, because if I take the common quantity as reference vector, it is very convenient for me to add or to obtain the resultant vector where the component vectors of that resultant vector are distributed across each component. So in case of series circuit, current remains common, hence I take current as reference vector, whereas voltage gets divided across each component as they are series. Therefore the resultant can be calculated for voltage by adding the the voltage drops across each component based on their phasor existence or based on their vector positions. Okay. So let us draw the vector diagram for the circuit. Current I is flowing through R. Okay. So first we will take current I as reference vector. Now we know current I is flowing through R, creating a voltage drop of ER across it. So in a resistance component or in a resistive component, the phasor relation between voltage and current are in phase. So already I have the vector of current as a reference vector. Therefore the voltage across resistance, which is ER, that is I into R, will be in phase with the current I. Okay. So that I will draw current that is voltage ER in phase with current I. Okay. So this shows the overlapping vector shows that voltage ER and the current I are in phase. Now coming to the inductive component, current I is flowing through the same current I is flowing through inductance L, creating a voltage EL across it. Please remember, this EL is not the voltage drop, it is the self-induced EMF that is created across L, okay, due to the alternating current creating the alternating flux in the inductance. Because this EL is opposing the source voltage, because as per the Lenz's law, I consider this EL to be a drop. Therefore XL I assume analogous to resistance R, where I can represent the voltage across L, I into XL, exactly in the same way I represent voltage across R as I into R. So with these representation of current multiplied by some quantity as the voltage across these components will give me a very convenient linear equation for the solution. Okay, or else if I exactly write the voltage across L and C, that become a differential or integral differential equation. Okay, will not go into that, which is not necessary for us in basic electrical engineering subject. Okay, so I have drawn voltage across the resistance, that is ER, which will fall in phase with the current. Now the current through L is same current I, and voltage across L is EL. So by the nature of inductance, know that current in inductance will be always lagging behind its voltage by an angle 90 degrees. But now already I have the current vector, therefore I need to place the voltage vector with respect to this current vector. So when I say that the current inductance lags behind voltage by an angle 90 degrees, I can also say the voltage across inductor leads the current by an angle 90 degrees. Because I have already the current vector positioned at a reference axis, now I will be placing the voltage vector EL leading the current vector I by an angle 90 degrees. So this diagram shows two vectors ER across R and EL across L positioned with respect to the current I. Okay. Now coming to the third component C, capacitance, the voltage across C is EC, whereas current through C is the same current I that has flown through R and L already. Now this current I vector is already lying on the reference axis. Again I have to fix the position of the voltage vector across C. Again you please recall that the voltage across capacitor is not the voltage drop, it is the voltage that is charged across the capacitor plates. Okay, like I discussed in the previous RC circuit lecture, that the left plate will be charged with positive potential, that is higher potential, and right plate will be charged with lower potential. When the potentials are marked, we see that the capacitor voltage EC will be opposing the source voltage E. Hence I consider the voltage across capacitor to be the drop across capacitor. Okay. Again I represent this drop or the voltage across EC analogous to voltage drop IR, where I take the help of capacitor reactance XC to represent the voltage across C as I into XC. Okay. Now with respect to the capacitor, we know the nature of capacitor, the phasor relation in capacitor is such that the current will be leading the voltage across capacitor by an angle 90 degrees. Now current I is already existing on reference axis in the form of a vector. I need to fix the voltage vector the capacitor, that is EC will be lagging behind the current I by an angle 90 degrees, because in capacitor current I has to lead the voltage across it by an angle 90 degrees. Now current I is already on reference vector, therefore I can take voltage lags behind the capacitor, lags behind the current by an angle 90 degrees in capacitor. Okay. So that vector is given by. Okay. So this is the vector diagram for this circuit. So please note the vector EL is larger than the length of vector EC, because it is the first case consideration where the XL is considered greater than XC, Hence EL is greater than EC, I into XL is greater than I into XC. Therefore, to represent this greater than relation, the length of vectors or the magnitude of vectors should also be represented accordingly. I simply cannot take the length of these two vectors equal, or length of EL less or length of EC larger than EL. Okay, so when I draw the vector diagram for any circuit, the length of vectors must be representing the corresponding values those are there in the circuit. Okay, though I may not draw the vector diagram to the scale, but at least the magnitudes of the vectors I take into the vector diagram should be giving a meaning to the magnitudes of the values those are there existing in the circuit parameters. And this is the same vector diagram what we have seen in the previous slide. Now this is the vector diagram for the circuit, okay, for RLC circuit when XL is greater than XC. Okay. So here we observe that the resultant voltage E is drawn in such a way that we can observe before that we can observe here the vector EL and EC are exactly opposite to each other. The nature of inductive reactance is exactly opposite to the nature of capacitive reactance. So therefore the vectors of EL and EC are opposing each other, or we can say these two vectors are out of phase by an angle 180 degrees. So the angle between EL and EC is 180 degrees. Okay. So the resultant vector E, okay, should be drawn in such a way that I should deduct the value of EC from EL. Hence my remaining vector will be EL minus EC. Okay. So because these two vectors are opposing each other, exactly opposing each other, the resultant of these two vector is EL minus EC. So this part, okay, this part is nothing but the deducted part of EC. So this remaining part what we observe is EL minus EC. So resultant voltage E is equals to I into Z, which will be leading the current I by an angle phi. So from this vector diagram it is very much evident that the nature of circuit is inductive. Okay. So when XL was greater than XC, that itself decided the nature of circuit inductive, but from the vector diagram also it is justified that the nature of circuit is inductive, because we observe voltage is leading the current by an angle phi, or current is lagging behind the voltage by an angle phi. That happens only in inductive circuit. Okay. So therefore when XL is greater than XC, the circuit behaves inductive. So whereas EL minus EC is given by I into XL minus I into XC, or I into XL minus XC. Therefore the instantaneous value of current is given by I equals to Im sin omega t minus phi, because I have taken E equal to Em sin omega t. If the initial phase angle of E is 0, therefore the initial phase angle of I is minus phi, that is phi lagging behind 0 with respect to the voltage. Whereas the resultant voltage E is nothing but E equal to I into Z, or under root ER square plus EL minus EC square. So from this Pythagoras theorem we can get the value of E is equal to under root ER square plus EL minus EC square. Okay. By taking the impedance triangle out of the vector diagram, I can observe the triangle will represent R, XL minus XC and Z. Therefore Z is given by under root R square plus XL minus XC whole square. Okay. And power factor is given by cos phi equal to R by Z. So this is a common definition of power factor which we have seen in the previous lecture. It is the ratio of resistance to impedance of the circuit. Okay, so cos phi is equals to R by Z, this R by Z from this impedance triangle, where phi is equals to tan inverse of XL minus XC upon R. So the effective reactance of the circuit is now XL minus XC. There is presence of inductive reactance, there is presence of capacitive reactance in the circuit now, but since both inductive and capacitive reactances are existing simultaneously in the circuit and XL is greater than XC, that is the inductive reactance is more effective than the capacitive reactance or more prominent than the capacitive reactance. Therefore, the resultant reactance or the effective reactance of the circuit is XL minus XC. Therefore, angle phi is given as tan inverse of XL minus XC upon R. Okay. The power consumed by the circuit is common, P equal to AI cos phi. Okay. So P equal to AI cos phi is general equation for power consumed in any AC circuit. Coming to case 2, when XC is greater than XL, that is capacitive reactance is greater than inductive reactance. Again, considering E equal to M sin omega t, that is initial phase angle of voltage to be 0, and taking voltage as the reference, voltage with reference phase angle, that is omega t equal to 0. Okay. Now when XC is greater than XL, obviously EC will be greater than EL. Okay. EC will be greater than EL because I into XC is greater than I into XL. Again, same current I is the common quantity that is flowing in all the resistance, all the components. Hence, my I into XC will be greater than I into XL. Okay. To draw the vector diagram for the circuit, again considering I as the reference vector because I is common in all the components, so I take I as a reference vector. This current I will flow through the resistance R, creating a drop ER. Therefore, as per the nature of resistance component, the current and voltage will be in phase. Therefore, the voltage ER will be in phase with the current I that is flowing through R. So, the second vector represent ER equal to I into R, which is in phase with the current I. Okay. The same current I will be now flowing through L, creating voltage EL across that, and as per the inductance component, the current I through the inductor will be always lagging behind the voltage across it, or voltage across inductor will be always leading the current through it. Therefore, EL will be okay. We have taken EC first. The same explanation will hold good. Current I will be flowing through C, creating a voltage across C to be EC, and with respect to the capacitor, okay, current will be always lagging behind the voltage, so leading the voltage by an angle 90 degrees. So current I is leading the voltage EC by an angle 90 degrees. Okay. Therefore, EC will be lagging behind the current I by an angle 90 degrees. Please remember that all these vectors are revolving or rotating in anti-clockwise direction at omega radians per second angular frequency. Okay. Now EL is the voltage across inductance which will lead the current through inductance by an angle 90 degrees. Okay. So EL is leading the current by an angle 90 degrees, or current is lagging behind the EL by an angle 90, and current is leading EC by an angle 90. Again, we observe here EL and EC come exactly opposite to each other, and observing the length of vectors, we see here that EC is greater than EL because XC is greater than XL. Therefore, vector EC is more lengthier than vector EL. Hence, the resultant vector is given by what we have done in the previous vector diagram, that in previous vector diagram we deducted EC from EL. Now we are deducting EL from EC. Sorry, there is a missing EC here. Here I should be writing EC. Okay, so I have to deduct this amount of EL from this EC. Hence I will get the remaining EL minus EC. which is equals to I into xi minus I into xl or I into xc minus xl. So the resultant E is given by under root the ER square plus EC minus EL square. Okay. And now the current here is leading the voltage E by an angle phi. Therefore I equal to Im sin omega t plus phi. So current I leads the voltage by an angle phi. Here the effect of the circuit is having the capacitive effect as Xc is greater than XL, hence current will be leading by an angle phi. Okay. From the the impedance triangle, I will take out the impedance triangle from this vector diagram. I can write as Z is equals to R square plus Xc minus XL whole square, and power factor is given by cos phi equal to R by Z. Okay, and phi equal to tan inverse Xc minus XL by R. Now the effective reactance of the circuit is Xc minus XL because Xc is greater than XL. Power consumed by the circuit is P equal to A cos phi. Okay. So for any AC circuit, power consumed is always P equal to A cos phi in single. Now considering case 3, the same circuit RLC with E equal to M sin omega t, that is taking the initial phase angle of voltage to be 0 degrees. Okay. Now if XL is equal to XC, now a point where the inductive reactance is equal to capacitive reactance, then what happens? My EL will be equal to EC or I into XL will be equal to I into XC. Okay. So when I draw the phasor diagram for this circuit, okay, by drawing vector diagram for this circuit, I can observe again current I will remain common in all the components, hence I take current I as the reference vector and I draw all the vectors remaining with respect to this current I. Okay. Now current I is flowing through R, therefore ER will be in phase with the current I. ER is in phase with the current I. It is flowing through L. Okay. So current I will be lagging behind EL by an angle 90, or EL will be leading the current I by an angle 90. So EL is leading current I by an angle 90 degrees. The same current I is flowing through capacitance C, hence it will be creating a voltage across it as EC volts. Therefore this current I will be leading the voltage EC by an angle 90 degrees, or voltage EC will be lagging behind this current by an angle 90 degrees. So therefore EL leads the current by an angle 90, EC lags the current by an angle 90. Now here observe the length of these vectors. These length of vectors are exactly equal because XL is equal to XC, therefore my EL is equals to EC. Hence the two vectors are exactly opposite to each other. The effect of these two vectors will cancel out. Okay. Therefore the resultant voltage is nothing but the voltage across the resistance. So ER is equals to E, hence the resultant voltage is in phase with the total current or the circuit current, hence the effect of this circuit is resistive. So when XL is equals to XC, my circuit behaves resistive, and we see from this phasor relation that even the total voltage E will come or will fall in phase with the circuit current I. Therefore I is equals to Im sin omega t. So there is no phase difference between voltage and current in this case. So when inductive reactance and capacitive reactance become equal, the phase angle difference between voltage and current becomes 0 because both the effects will cancel out. Okay, hence my voltage and current will fall in phase and the current will be equals to Im sin omega t. This should come out to be the small I. Mistakenly I have written I equal to Im sin omega t. It should be small I equal to Im sin omega t. I think in the previous slides also I have made the same mistake. Please make note that this capital I should be replaced by small I. Okay. So I is equals to Im sin omega t. Therefore the initial phase angle of current is also 0 degrees. Okay. So taking the impedances, the reactances out. I can't get a triangle here. I will not get a triangle here because there is no resultant. The resultant will be in phase with the reference vector. The effect of XL is cancelled out by effect of XC. Okay, that is inductive reactance cancels with the capacitive reactance. Therefore, the nature of circuit remains only resistive. Okay, so the total or the effective impedance of the circuit is equal to the resistance of the circuit. Okay, therefore, as Z is equals to R, power factor cos phi is given by R by Z as per the previous power triangle. Now it will be R by R equals to 1. As cos phi equals to 1, angle phi is equals to 0 because XL minus XC or XC minus XL will be 0. So tan inverse of XL minus XC by R will be 0 by R, that will be tan inverse of 0, which is equals to 0 degrees. So the phase angle difference between voltage and current does not exist, it becomes 0. The power consumed in the circuit is given by P equal to EI cos phi. Since cos phi is equals to 1, power consumed is equals to P equal to EI. That means that the power consumed in the RLC circuit when XL is equal to XC is equal to the total power or the apparent power given to the circuit. The complete power given to the circuit is consumed by this resistance, or it is work done in this resistance. The reactive powers will disappear because the reactive power of inductance will cancel out with the reactive power of capacitance. So the total power consumed is equal to, the power consumed is equal to the total power, as the inductive reactive power is neutralized or cancelled by the capacitive reactive power. Okay. So this is the analysis of RLC series circuit. Because of the existence of capacitance as well as inductance, the effect of capacitance, the effect of inductance should also, and the effect of resistance is been analyzed. So with this we will come to an end of the series circuit analysis. Okay. I hope these lectures videos were helpful to you in understanding the circuit analysis or series circuit analysis. Please go through these videos once again, and you can refer any textbook, okay, for studying the contents of this lecture, whatever we have covered so far. Okay. So in the lecture, okay, we will be solving few numericals on this series circuit. We will be seeing few examples, and after that we will deal with the parallel circuit analysis. Okay. So